Welcome back. We're going to be looking at a concept called equilibrium today. This is section 18.2. Within this lecture I have a couple demonstrations to share with you. One of them you've seen before, it's with bromothymol blue. I have a demonstration to share the concept of equilibrium and then a chemical reaction that the equilibrium is changing due to temperature. So those are some of the things that we're going to be taking a look at with this concept of equilibrium. Before we begin, you should probably have a little bit of an understanding of what equilibrium means. And we have equilibrium. When you're standing, you have this equilibrium control within your body. If you want to do this demonstration, you can go ahead and do it by yourselves. If you can just listen to this, and if you can just stand up right now. So I'm going to be standing up and doing this along with you. And we have many different controls for our balance or equilibrium. There's one in our ear, there is one in our eyes, and there's actually control of our balance in our legs. So those are the three things we're going to be taking a look at right now. So if you want to do this demonstration, go ahead. If not, you can go ahead and just kind of fast forward, but it's kind of fun. What I'd like you to do is I want you to stand up on one leg, either your right or left, and what you'll may notice is that your muscles have these very fast twitch type of reactions, and these are muscles that are being triggered to flex because we have these things called proprioceptors, and they sense when other muscles are moving and we're off balance, and those automatically adjust for us. So you feel kind of this twitchiness. Another control for balance actually is in our eyes. So right now, while you're standing on one leg, I'd like you to now close your eyes, and I'm becoming a little bit more wobbly. I don't know about you. You can't be holding on to anything, and I've lost my sense of equilibrium or balance because my eyes have lost the horizon. So removing that, we actually have problem keeping our balance. Now the third one is in our ears, and we have this little calcium disc called an otolith inside our inner ear, and that shifts left and right, and that tells us when we're off balance as well. So stand on one leg, close your eyes, and if you're not already off balance, then lean your head either to the left or to the right, and you're probably going to fall over. Okay, so that is equilibrium with our bodies. Let's take a look at what this is with chemistry. So with equilibrium, we're going to be looking at what's called a reversible reaction. And we'll get to the definition of the reversible reaction. Here is an example. We've seen this before as well. If you take water, and if we add carbon dioxide, CO2 to that, what happens is it becomes an acid. And the acid that it becomes is H2CO3. It's a combination reaction, and it forms carbonic acid. Remember, all acids begin with letter H. However, carbonic acid doesn't really like to stay in this form. It actually prefers to be back in this form. So once this is made, it actually falls back apart again into this right here. So here's the example. I've got 2 flasks of the bromothymol blue. We've done this in class, you've probably done this in biology, and I'm going to go ahead and blow in this one for a couple of breaths. And if you don't want to hear me breathing, you can go ahead and fast forward till you see something happening again. Okay, I need more breath. Still breathing. Okay, so now we have a reaction, and this is what it looks like now. This is what it started at. So what's happening in this is we're going to be looking at this next chapter. What's happening is I am introducing my carbon dioxide. It's actually creating an acid. And this acid reacts with the blue stain. And a major theme we're going to take a look at next chapter is going to be when you have these indicator stains and they react with acids, they change their shape. You chemically alter their shape, which then is going to change their color. It changes the way that they can absorb and reflect light. So if you have a different colored stain, it's going to be a different type of color. So what I've done is I have introduced the carbon dioxide and I have made carbonic acid and has changed this. But as I said earlier, it doesn't like to be in this form. Even as we speak right now, all the carbon dioxide that I breathed in is going to begin to escape. So it's now escaping out through the top of this flask. If you let this sit, come back 24 hours later, it will look very much like this right here. So we have this concept of a reversible reaction. They can go forwards and they can also go backwards. That's what it means to be reversible. Now, in its balanced form, not all 100% of this will fall apart into this. If we let it sit and come back tomorrow, there'll be about 1% of carbonic acid, and the other 99% will have gone back to the original state. This is now in its balanced form. This is when it is at equilibrium. It is now balanced. So I want to go through an example of what it sort of means to be balanced and at equilibrium. So imagine that we have 10 pieces of A and 10 pieces of B, and we're going to be forming the compound AB. So we haven't really formed anything as of yet. Okay? So what we're going to do is we're going to allow A and B to form with each other. And so we're going to take one of A, one of B, and we combine them together. It's going to make one AB. Since I took one of these and one of these, I'm left with now 9 pieces and 9 pieces. Okay, we're going to do the same thing. We're going to make another AB. So we're going to pull one from here, which means I now have 8 and 8, and then I have 2. Let's do another one. We're going to make another one. We have 7 and 7, and we form 3. So we made 3 ABs. We did that by taking 3 A's and 3 B's. We made this. Now what happens next is, well, this 3 is going to fall apart back into A and B again. We have 8 and 8, and then 2. And then these will try to make the AB again, and then we'll have 7, 7, and 3. So we have the starting scenario where we have 10 of each, and then we have this fluctuation back and forth where we have 8 and 7, and we have 2 and 3. This right here, this is the state of equilibrium. We now have reached equilibrium. So what does it mean to be at equilibrium? Let me give you the definition for this. Here's the kind of formal definition, and then we'll get to a simpler definition as well. So equilibrium is when the number of reactants, in this case it was the A and the B, when the number of reactants that are becoming products is going to be equal to, I'm going to go back here, the number of products that are becoming reactants. So let me explain this again. So going back to the number of reactants here, we have reactants that are becoming products, and we have one of each becoming the product. Okay, then this falls apart, the product falls apart, and it produces one of each to go back to the reactants. The number of reactants becoming products is equal to the number of products becoming reactants. Another way of saying this is we have a forward reaction, we have a reverse reaction. And so we have the forward rate. The forward rate is going to be equal to the reverse rate. That's another definition for equilibrium. So let's take a look at another example that I have, and I'm going to be using this little tablespoon, and I've got these metal spheres. Okay, so I had one metal sphere, and into this, we have to make an assumption that when it's in my hand, it's the reactant. When it gets into the tablespoon, it becomes the product. So I've formed a product. Take a reactant, I've formed a product. I'm taking a reactant, I'm forming a product. I'm taking a reactant, forming a product. Can you see where this is going? Taking a reactant, forming a product. Reactant 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 forming a product, 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 reactant forming a product. So as I put the reactants in, they're falling apart, and the products are falling apart, becoming reactants. So I put a reactant in, another reactant goes in, and two fall out. One goes in, another one. Okay, so you can see what's happening is that we can only form a certain amount of my product before it begins to fall out and it becomes the reactant again. So I hope that demonstration helped a little bit with that as well. So that is equilibrium. So let's take a look at one of the scientists. His name is Le Chatelier. He was studying equilibrium, and he came up with this concept of manipulating the system. For example, if I breathed excess carbon dioxide into the water, it became this, and I manipulated the system, and therefore it created a new scenario, a new system, and then it wanted to get back to the original. So Le Chatelier's principle is this: if you change the system, you change the equilibrium. Okay, so I'm going to draw this as a series of balances and rulers. So here we have the carbon dioxide and the water forming the carbonic acid again. And if you can draw a ruler and imagine that it's being suspended and it's in complete balance. So here's my ruler, and it's completely balanced. Okay, what is that balanced state? That balanced state is where it's 1% carbonic acid and where it's 99% the reactants, water and carbon dioxide. Now, Le Chatelier says if you change the system, you change the equilibrium, and it wants to get back to this balanced state. What I was doing is I was having this massive influx of carbon dioxide. Well, if I'm putting in excess carbon dioxide, I'm increasing this 99%. Maybe it became 99.9%, and this became 0.1%. Okay, it wants to be in this state that it is right now, so it's going to get back into its old state. So let's draw this. I'm now going to be breathing in and increasing the amount of carbon dioxide. So I'm increasing my reactant. So remember, here are your reactants. Your reactants over here, and here are your products, your end product, your starting reactants. So I'm increasing this. So imagine that this is like, sorry about the lights. Imagine that this ruler has now, that was in balance, is now going to be out of balance. So let's draw this. I'm increasing the reactant, and so the ruler would look something like this. I've increased the amount of carbon dioxide. Now imagine you have a little ball, that's going to roll. Previously, it was nicely balanced and just sitting there. What's going to happen to this ball? This ball is going to roll down the ruler. So if it rolls down the ruler, what it means is that we've increased the carbon dioxide. This is going to make the reaction go forward, or downhill in this case. It's going to be going down, forward, and it's going to make more of this. So if I put the carbon dioxide in, it's going to make more of my product in order to balance the reaction. So if I make more of this, it'll eventually cause the reaction to go back to being balanced again. So again, if you put the increased carbon dioxide, the reaction is going to go forward. So if you imagine reading you go from left to right, so it's going forward, this would be backwards. Go back to up here, this is the forward reaction, this is the reverse reaction. Okay, we can also say the reaction goes to the right direction. It goes to the right. And we can also say the reaction favors, if I put an influx of all these reactants, it's going to favor the other side, and it's going to favor the products. Okay, now let's say that I was taking out the carbonic acid over here. Let's say I decrease this amount over here. Now I have less than 1%, but we want to get back to 1%. We want to get back to that balance. So let's say I decrease the carbonic acid. So if you can draw this ruler again, now I'm not increasing the reactants, I'm not increasing the products, I'm actually decreasing the product. So if you can draw this ruler like this, I've now decreased the carbonic acid, the H2CO3. Again, which direction is the ball going to roll? It's going to be rolling forward. We would say the reaction goes forward. So again, if I take out H2CO3, there's not enough to be in balance. So what happens is these reactants will combine to form more of this so that it goes back into equilibrium. So we've disturbed the equilibrium again. It wants to get back to equilibrium. And it's going to do that because you decrease this. We're going to be taking the reactants and we're going to be making more of those. So here again, the reaction is going to go to the right. And the reaction would then favor the products. So again, if you remove the products, we need to get more of them. So the reactants will combine to make more. Let's say I decreased the water. Okay, is water a reactant or a product? It's a reactant. So let's draw our ruler. And again, here's my reactants, here's my products. I've decreased my reactant, or one of my reactants. I decreased the amount of water. Well, if the ball is over here, what's going to happen to it? It's going to go backwards. So we would say the reaction goes backward. The reaction goes not to the right, but reaction goes to the left. And if I decrease the amount of water, let's say now I have 98%, I need more to be back in balance. So my product is going to fall apart to make more and to get that back up to the 99%. So the reaction is going to favor the reactants. Okay, hopefully that makes a little sense. We can talk about that if it doesn't. So that's by changing the concentration. So here's the concentration. Concentration changes the equilibrium. We can also have a scenario where we have temperature. And temperature is going to change the equilibrium. Okay, so in this example, I need to get a pair of gloves, and I'm going to be using a substance called cobalt chloride. I may be using gloves here because cobalt chloride is carcinogenic, meaning that it can cause cancer. So if it spilled on me, it wouldn't make me have cancer, but it would increase my risk of getting cancer. So got my gloves on for this reaction, okay? So here is what we're starting with. We're starting off with cobalt chloride, and we're going to be ending with cobalt chloride and water. Notice how heat, so we're looking at temperature now, not concentration, but temperature. How does temperature change the equilibrium? Well, in this reaction, heat is actually going to be a reactant. Let me show you what the cobalt chloride looks like. Okay, it is this blue stuff, and I'm going to keep this right here as our control, so you can kind of see what it looks like. Okay, and what we're going to do is we're going to be putting this in a beaker with some hot water. So this is at equilibrium, the cobalt chloride, and it's a pentahydrate plus heat. So these are my reactants. What's going to happen is we're going to be ending up with a dihydrate and 3 waters being produced over here. But look at what also happens. This is sort of like a crystal structure, and when it's all bound together like this, the color is pink. But when you have a dihydrate, it's going to change its shape. And when it changes its shape, it's going to be changing its color. So yes, it's already in its blue state. Okay. So what we're going to do is I have a hot and I have a cold. Here is some ice water, and I've had some on the hot plate sitting over here. Here is the hot water. You can see some of the condensation along the sides. So what I'm going to do is I'm going to have this as my control over here, and I'm going to be putting in the cobalt chloride into the hot water over here, and I'm going to be putting it into the cold water over here. We have to wait for a short while for this to take place. So we're just going to let this sit for a couple minutes. I'm seeing some changes already with the hot, and we'll take a look at the cold in just a minute. So here is the original. Here is the, let me go ahead and put this right here. Okay, this is the control. Okay, now when I put it in the hot, what we see is this, and you can see that it got darker. Okay, let me try to show you here. Here's the original control. This one got darker by being added to the heat. Okay, so that happened with the heat. Well, what happened with the cold? So here's my control. Let me keep this all straight. Here is the hot that got darker blue. Here is the control, and I don't know if you can see this, but it has turned a slight pinkish, light purple color. Let me put it down like this. You might be able to see. There you go. So you can see a little bit of a pinkish hue to that. Okay, so let's take a look and see what's happening with this scenario. Okay, control, there's my hot, here's my cold over here. Okay, what's the color of the solution above the water compared to the control? So this is the hot vial. There's some other dynamics that we really can't discuss because you guys aren't here to see it. But this color right here, it turned a dark blue. So right there, this color turned dark blue. Okay, it started off a lighter blue and it went to a dark blue. Okay, so we're going to be skipping this. What color solution do we have here? This one turned into a light pink. Okay, we're not going to answer these questions, but let's take a look at the control. Let's put the control over here. The control was light blue. Let me go ahead and actually, I think it's safe to take those gloves off. Okay, so let's take a look at this. So we're at room temperature, so let's go ahead and draw our diagram like this, room temperature. Actually, we're at equilibrium right now, so the reaction is not going to go either direction. It's It's a reversible reaction. It's not really moving, so we don't have to worry about this right here. So what's happening now is in the first scenario, we're increasing the heat. Well, heat is a reactant. Which way am I going to draw my ruler, my balanced ruler? It's been thrown out of balance. Okay, so I now have changed the equilibrium by increasing the reactant. So your ruler would look something like this. Okay, I've increased the heat. I've increased the heat, I've increased the reactant. What's the ball going to do? It's going to fall down this direction. Therefore, the reaction is going to go forward. Well, if the reaction goes forward, it's going to be producing something that's very blue, and actually that's what happened. When we had the hot, it became dark blue. So the reaction goes forward, the reaction goes to the right, and again, the reaction favors the products. Let's do the reverse scenario. I cooled it. So what was happening to my heat? I was actually taking the heat away. So I'm removing the heat, I'm removing a reactant. How would that be drawn? Okay, I am now decreasing the heat. I am decreasing the reactant. Well, it was previously at equilibrium. Now that I removed the heat, I have changed the equilibrium. It wants to get back to the original state. So it wants to be back balanced. Well, how does it get back to being balanced? Well, what's going to happen is we're going to have the product fall apart and become more reactant. So we'll get less of this and more of this, and it's going to be balancing back out again. So if we decrease the heat, the reaction will go in this direction. The reaction goes not forward, but it goes backward. The reaction goes to the left. Left. The reaction is going to favors the reactants. And since it's going to the left, it's going backwards, it's going to turn then pink. So that is the fluctuation of equilibrium with temperature. Now let's see what happens with pressure. Okay, imagine you have a giant piston. So here's a piston right here. Okay, and this is filled with just air. And I am then going to apply pressure. And when I increase the pressure again, you can see the volume is increasing. Okay, it doesn't like to stay like that. I can feel it pushing back. It wants to be back right here. So this is actually the equilibrium state for this setup right here. So imagine that I have a combination of different gases on the inside, and what we're going to be looking at is we're going to be taking a look at nitrogen, and we're going to be taking a look at hydrogen, and these can form ammonia gas. This is a reversible reaction. The ammonia can fall apart to produce the hydrogen and also the nitrogen. Let's count how many moles of material that I have in here. If we look at the balanced reaction right here, I have 1 mole of nitrogen because I'm looking at the coefficient. So I have 1 mole of this, okay, plus 3 moles of this, and this produces 2 moles of the product. So I have 1 plus 3, I have 4 moles as reactant, and I have 2 moles as product. Now, for this, you have to remember the mole box. Okay? So, remember the mole box. Well, what's inside the mole box is 6.02 times 10 to the 23rd particles. It's 1 mole of gas. Okay, so imagine I have 4 boxes as reactant, And it can also become 2 moles as well. So I have 4 boxes and I have 2 boxes. So this is now at equilibrium and it's just sitting there. And what I'm going to do is we're going to now push this piston down. Okay, so if I push the piston down right here, what has happened? I have increased the pressure. Okay, so if I increase the pressure, it's going to decrease the volume. Look at how little space that I have right here. Okay, now go back to this. Which is going to be better surviving in this less space? 4 boxes of a gas or 2 boxes of a gas? Which is going to more easily fit in this smaller space? 4 boxes or 2 boxes? The answer is 2 boxes. So because we've decreased the volume, we have less space. Because we have less space, the 2 moles is going to fit in there more easily. 2 moles fits better. So if we increase the pressure, is it going to favor the reactants or the products? So because we have less space, 2 moles fits better. This is going to favor 2 moles, which is the products. Now, this only works with gases. This doesn't really work with liquids, and it doesn't work, of course, with solids. It's because gases have space and can be compressed. So here's another factor. So we're looking at pressure, and it's only applied to gases. So let's do the opposite scenario. Let's say we're at equilibrium right here. Here's our equilibrium state. Now what we're going to do is we're going to decrease the pressure. We're going to be taking this piston up. So if we decrease the pressure on this, what happens to our space? We can see that it's going to increase the volume. Which is going to better fit in this space? The 4 moles or the 2 moles? Well, now that we've created this extra space, the 4 moles is going to have an easier time fitting in here. So we have more space, and the 4 moles fits better. And because the 4 moles fits better, is it going to favor the reactants or the products? This is going to be going to the left. It's going to favor the reactants. It's going to favor the reactants. It's going to be a backward or reverse reaction. Forward reaction, reverse reaction. So equilibrium is when chemical reactions maintain balance. They need to be reversible reactions. This can't happen with a non-reversible reaction. It has to be reversible. And when we have reversible reactions, each chemical reaction has its own equilibrium. And if you alter that equilibrium, either with concentration, with temperature, or pressure in gases, you're going to change the equilibrium. And it will want to get back to its balanced form. And it will either favor the reactants or it will favor the products, depending upon which direction that you've altered it. I hope this makes sense. We can also talk about this later.